Here we will finish up our look at reactions and reactive species by talking about allylic and benzylic radicals. Last semester we talked about a number of different reactions involving halogens, so let's review some of what we've seen. If we have an alkane and we treat it with bromine, well, we actually get no reaction. Remember, if we want a reaction to happen, we have to use light and or heat, because the light and heat will cause bromine to undergo homolytic dissociation to give two bromine radicals, and then a bromine radical can abstract a hydrogen from, in this case, cyclohexane. That puts this electron on the ring, giving us this radical, and then this radical can bump into another molecule of bromine, right? There's very few radicals around, so it's much more likely that a radical will bump into a molecule rather than a radical bumps into a radical. So this can abstract a bromine, and then we generate another bromine radical. So this gives us a substitution where bromine has substituted for a hydrogen, and this proceeded through a radical mechanism. So what we have here is an initiation step followed by a propagation step followed by another propagation step. And so these propagation steps will happen again and again and again in a chain reaction until eventually radicals do bump into each other in a termination step. Now, what if we have an alkene rather than an alkane? So if we have an alkene and we treat it with bromine, this is going to give us a different product. We're going to make a dibromide. This proceeds through electrophilic addition. We get the dibromide plus its enantiomer. So remember, this one proceeds through the cyclic bromonium ion, and then Br- can attack from the back, opening up the bromonium ion, leading to this compound shown here. Or if the Br- attacks this position, then it will open up the other way, leading to the enantiomer of what's drawn here. Now, it's also possible for an alkene to undergo radical halogenation as well. If this is treated with bromine and heat or light, then it is possible to make a benzylic bromide. Sorry, that's an allylic bromide. Once again, this plus its enantiomer. Now, this would be a little bit risky, so if we treat it with bromine, are we going to get electrophilic addition or are we going to get radical halogenation? So rather than just treating it with bromine and hoping you have enough heat, there are specialized reagents that have been developed. So a common one is called NBS, which is N-bromosuccinimide, which looks like this. And this is a source of bromine, which in turn is a source of bromine radicals. And so that causes a radical halogenation, which happens at the allylic position. So the halogenation will occur here or here, not right at the alkene carbons and not at the carbons that are further away. Why is that the case? So if we think about these hydrogens compared to these hydrogens, if they interact with a bromine radical, if the bromine radical was to try to grab off one of these hydrogens, that has a bond dissociation energy of about 410 kilojoules per mole. But if the bromine tries to grab off one of these hydrogens, That has a bond dissociation energy of only 370 kilojoules per mole. So this one is definitely favored. So what does that give us? We have an allylic radical. So one hydrogen is still there, but we are left with a radical. Why is this special? Because of resonance. We can imagine that this electron moves here, and one of these electrons moves here, and the other one of these electrons moves here onto this carbon, and that gives us another resonance contributor that has a double bond here and a radical here. So abstraction of one of these hydrogens is preferred over abstraction of one of these hydrogens because it's easier, because the resulting radical is stabilized by resonance. After this radical is formed, then it can react with a molecule of bromine. Let's say this grabs off the bromine, forming another radical. So we get this and another bromine radical, which can repeat the abstraction over here. So a number of different types of reactions can be happening. If we have an alkane, then treatment with bromine or chlorine and light and heat is going to lead to radical halogenation, in which a hydrogen is replaced by a bromine. If we have an alkene and we treat it just with bromine so that there are no radicals forming, this will undergo electrophilic addition to give a dibromide. But if we treat the alkene with NBS, we might see NBS plus peroxides, we might see NBS plus heat, but just look for NBS. That is going to give us radical halogenation, leading to the allylic halide. The good news is we have a new reaction in our synthetic toolbox, which gives us even more flexibility to be able to take a particular starting material and convert it to something different. The bad news is there are some limitations. Now with this particular compound, notice we have two different allylic positions. We have this allylic position where we have two hydrogens, and we have this allylic position where we have one hydrogen and a methyl group. So what happens if this compound is treated with NBS in the presence of light, which will serve as a source of bromine, which serves as a source of bromine radicals? One possibility is that this allylic hydrogen is abstracted, and that will lead to this radical. And with this radical, we have another resonance structure that looks like this. Now, if we think about reaction with bromine, then this can abstract the bromine, and that will lead to this, or this one can abstract the bromine, and that leads to this product. And so two different products can be formed. But that was only looking at the first allylic position. Now what if one of these hydrogens is abstracted? Then that will lead to this radical, which is in resonance with this radical. If reaction with bromine occurs at this position, we get this. But if reaction with bromine occurs at this position, we get this. In other words, we get a mess, right? So this one is 3-bromo, 3-methyl cyclohexene. This one is 3-bromo, 1-methyl cyclohexene. This one is 3-bromo, 6-methyl. And this one is 3-bromo, 4-methyl. So we get a mess, okay? We get a mixture of products, and that's just with regiochemistry, right? We also will have stereochemistry as well. So this is really a mess. The good news is we do have a new method, a new reaction that can be carried out that gives us allylic halogenation. Bad news is it only works with symmetrical allylic positions. Okay, so we have to watch out for that. What about benzylic halogenation? If this compound is treated with bromine in the presence of light or heat, this is the major product that will be isolated, where the bromine is connected to the benzylic position. Just like what we saw for allylic halogenation, for benzylic halogenation, NBS can also be used. Once again, you might see NBS with peroxides, NBS with heat, but NBS is the important thing. So what's happening? NBS is a source of bromine, which is a source of bromine radicals, and so a bromine radical can abstract a hydrogen from the starting material. We have a lot of options. If it abstracts one of these hydrogens, that leads to the first radical down here. If it abstracts this one, that leads to the second one. If it abstracts any of these, it leads to this one. But we also have everything on the ring. So if it abstracts either of these, we get this radical. There are two other radicals possible because we could get abstraction of one of these hydrogens or this hydrogen right here. So out of these different options, let's focus on the first one because this one gives us a benzylic radical. So over here, this one is tertiary, this one is primary, this one, I don't even know what you would call it because it's right on the benzene, but this one is secondary and benzylic. Now because it's benzylic, that means we're going to have a lot of resonance, just like we saw with benzylic anions and benzylic carbocations. So we can imagine the movement of electrons where this one goes here and this one goes here. Remember, I'm trying to use the dotted line for these curved arrows because we're talking about resonance, which is the imaginary movement of electrons, right? Because the electrons don't really move like this, they just exist like this. That gives us this, and the radical is here. We have another resonance structure that looks like this. We have another resonance structure that looks like this. And then another resonance structure. Sorry, I know these are getting really hard to see. That looks like this. So because of so much delocalization of electrons, because we can draw so many different resonance contributors, the benzylic radical is significantly delocalized, which greatly stabilizes it. So this radical is going to be formed to a much greater extent than any other possible radicals. Unlike the problem that we had with the allylic radicals, though, even though these resonance contributors are going to contribute to the stability, abstraction of the bromine will only happen at this position. Okay, so we're not going to get a mixture because all of these would lead to loss of aromaticity. We can imagine that it's only this resonance structure that abstracts the bromine because we only get bromination at the benzylic position, giving us the product that we showed up here. So let's pull this all together, and we see that we have a variety of transformations that we can carry out. If we have an alkane, we can treat it, for example, with bromine in the presence of light and heat, and that will give a substitution by a radical mechanism. We have to have light and heat to get the initiation to happen. Keep in mind, bromine is very selective and strongly prefers a tertiary position. Chlorine is more reactive, less selective, so while it prefers tertiary, it will still give a significant amount of reaction at secondary or primary. If we have an alkene, if we treat it with HBr, for example, we will carry out electrophilic addition. The alkene will share its electrons with the hydrogen, resulting in the more stable tertiary carbocation, and then Br- will attack back again, leading to the Markovnikov product. If we treat this with Br2, it's another type of electrophilic addition, but this is going to lead to a geminal dihalide. And finally, if we treat the same alkene with NBS, this is going to give us allylic bromination. And finally, when it comes to a benzene-containing compound, treatment with NBS will lead to benzylic halogenation, so the reaction will happen only at this position. So in this chapter, we've discussed allylic and benzylic systems. We know why they are stable, we know how to identify them, and we know to be on the lookout for the different reactive species, whether we're talking about carbocations, anions, or radicals. Allylic and benzylic systems are much more stable, which means they can be formed more easily, which means the starting materials that lead to these intermediates are going to be much more reactive.